pause for 1 second. Before you hear another word of this, I want you to do something. Look at your hand. Really look at it. Every atom in that hand is older than the Earth. The iron running through your blood was forged inside a star that exploded before our sun existed. You are not on the universe. You are made of it. And tonight, the universe is going to show you something about itself that will make you question whether we understand anything at all. Because right now, in laboratories across the world, the most respected physicists alive are quietly saying the same thing. Our model of reality might be wrong, not slightly adjusted, not needing a minor correction. Wrong in a way that changes everything. The age of the universe, the size of the universe, what it is made of, how it ends, all of it now in question. And the crisis is not coming. It has arrived. Tonight we are going to travel from this planet to the absolute edge of everything that has ever existed. And what we find along the way will destroy every mental picture you have ever had of the cosmos and replace it with something stranger, darker, and more extraordinary than anything you were taught in school. We are going to discover that 80% of all space is essentially nothing. That the largest structure ever photographed was only first seen last year. That our best telescope is finding galaxies that cannot possibly exist under our current understanding of physics. That the Milky Way, our galaxy, our home, is falling through space toward something invisible at 2 million kilometers per hour and will never arrive. And that the universe you think you can see, all 93 billion light-years of it, may be so microscopic compared to what actually exists that describing the ratio would require numbers your brain physically cannot process. And at the very end, after all of that, we are going to ask the oldest question humans have ever asked. The one that keeps people staring at the night sky long after they should be asleep. And when we get there, you will understand why the answer might have nothing to do with biology, with chemistry, with the probability of life arising. The answer might be architectural. The universe itself might be designed in a way that makes the question permanently, cosmically unanswerable. If any of this makes you want to immediately pause and check that you are in the right place, you are in exactly the right place. Stay with us. This is going to change how you see everything. Let us start with a lie. Not a malicious lie, a perceptual one. One that the night sky has been telling you your entire life and will keep telling everyone who ever lives on this planet. Go outside tonight. Find a place with no city light. Let your eyes adjust for 10 minutes. What you will see looks infinite. Thousands of stars in every direction. The Milky Way arching overhead. It feels like you are looking at the whole universe stretched above you. You are not. You are looking at your neighborhood. You are looking at one tiny corner of one ordinary galaxy. And even within that galaxy, you are only seeing stars within roughly 1,000 light-years of Earth. The Milky Way is 100,000 light-years across. You can see 1% of its diameter. The other 99% is behind the glare, the dust, the sheer distance that light has not bothered to finish crossing. The Milky Way holds approximately 250 billion stars. On a perfect night, you can see 4,000 of them. That ratio deserves a pause. 4,000 out of 250 billion. If the Milky Way were a city of 250 billion people, you would be standing in a room seeing 4 of them and calling it a census. Now hold that feeling of scale, because we have not even left our galaxy yet. The observable universe contains somewhere around 2 trillion galaxies. 2 trillion. Each one holding billions or hundreds of billions of stars. the total number of stars in the observable universe is estimated at 10 to the power of 24. That is more stars than every grain of sand on every beach on every continent on this planet combined. And the night sky you have been staring at your entire life contains 4,000 of them. The night sky is not a window, it is a pinhole. But here is the part that should stop you completely. The scientists who study all of this for a living, the people with the most powerful telescope ever built, the most sophisticated mathematical models ever constructed, the combined intellectual output of human civilization pointed directly at the sky for generations. They are currently confronting the possibility that their model of the universe is broken. There is a number. It seems simple. It is called the Hubble constant. It measures how fast the universe is expanding. One number. Get it right, and the age of the universe, the size of the universe, the ultimate fate of everything makes sense. Get it wrong, and nothing does. For decades, there were two ways to measure it. The first method looks at the oldest light in existence, the cosmic microwave background, radiation left over from when the universe was only 380,000 years old, still a newborn. Measuring it with the European Space Agency's Planck satellite and running it through our standard cosmological model gives a value of roughly 67.5 kilometers per second per megaparsec. The second method does not use ancient light at all. It measures the universe directly, right now, locally, using known stars and known distances to calculate how fast nearby galaxies are flying apart. That method consistently gets 73 to 76, sometimes higher. The difference between 67 and 73 might not sound alarming. In precision cosmology, it is a catastrophe. And by late 2025, the gap between these two measurements crossed 5 sigma. In physics, 5 sigma is not a signal. It is not a trend. It is a discovery. 5 sigma is the exact threshold used to confirm the existence of the Higgs boson, the God particle, the fundamental piece of the standard model of particle physics that physicists searched for decades to find. The confirmation that shook the scientific world. Same threshold, same certainty. This disagreement is real. The James Webb Space Telescope went back and re-examined the same stars used in the local measurements to check for errors. Were they dusty? Was the data contaminated? The answer came back clean. The local measurements are correct. Then an entirely independent team used gravitational lensing, watching how light bends around galaxies, to calculate the expansion rate from scratch. Their number matched the local value too. Every new independent measurement of the local universe returns the same answer, and it is the wrong answer according to our model. Daniel Skolnick, a physicist at Duke University, said it plainly: "Our model of cosmology might be broken. We are pressing really hard against models we have been using for 2.5 decades and seeing that things are not matching up." Before you continue watching, ask yourself this in the comments below. If our fundamental model of how the universe expands is broken, what else are we wrong about? And what would it mean if we found out? We will come back to the Hubble crisis. But first, we need to travel. We need to feel the scale in our bodies before we can understand what the mathematics is trying to tell us. Because the distances involved are not just large. They are the kind of large that the human brain did not evolve to feel. And feeling them, even imperfectly, changes everything. Start close. The moon, hanging in the sky like it is almost reachable, 384,000 kilometers away. That is far enough to fit 30 Earths side by side between here and there. A rocket at escape velocity takes 3 days to reach it. A Formula One car at top speed would need 42 days. This is the closest thing to us in the universe. This is step 1 on the staircase, and it already takes 3 days going 28,000 kilometers per hour. Mars is next, the planet that dominates every conversation about humanity's future, our neighbor, the world we talk about colonizing. At its closest approach, Mars is 55 million kilometers away. At its farthest, over 400 million. A light-speed signal, the fastest thing allowed by physics, takes between 3 and 21 minutes to travel one way. When NASA sends a command to the Curiosity rover, they wait up to 21 minutes just to find out if it was received. A conversation is impossible. A phone call is impossible. Mars is our nearest planetary neighbor, and it is already beyond the reach of real-time communication. In 2014, the Curiosity rover turned its cameras upward and photographed Earth from the Martian surface. Our planet was a faint pale dot, not a marble, not a jewel, a smudge. Everything ever written, every person ever born, every war ever fought, every piece of music ever composed, reduced to a pixel in someone else's sky. And that was just from Mars. Now try to leave the solar system. Our fastest spacecraft, Voyager 1, launched in 1977, has been traveling continuously for nearly 50 years at 61,000 kilometers per hour. It is currently about 24.5 billion kilometers from Earth. No human creation has ever gone farther. And it has not left the solar system. Not even close. Beyond the planets and the Kuiper Belt lies the Oort cloud, a vast shell of icy debris extending perhaps to 100,000 times the distance from Earth to the Sun. Voyager 1 will reach the inner edge of the Oort cloud in roughly 300 years. It will take 30,000 years to exit the other side. 30,000 years. That is longer than every written record in all of human history. At the end of those 30,000 years, Voyager will have merely crossed our Sun's gravitational neighborhood. It will not have come close to a single other star. The nearest star to the Sun is Proxima Centauri, 4.2 light-years away, at Voyager's speed 73,000 years to get there. If Voyager had launched when the first cities were being built in ancient Mesopotamia, when writing was just being invented, when humans were first scratching records into clay, it still would not have arrived. Strapped to Voyager's hull is a golden record. A 12-inch gold-plated copper disc containing greetings in 55 languages. Music from Bach to Chuck Berry to Azerbaijani folk songs. Recorded sounds of earth, thunder, whale song, a mother and child, 90 minutes of audio and images representing everything we thought was worth saying about ourselves. It was designed as a message to whoever might find it. Carl Sagan chaired the committee that chose its contents. It is the most carefully considered letter humanity has ever written to a stranger. The probability of anyone finding it is so close to zero that the number is almost meaningless. Space is too vast. Voyager will drift through interstellar space for billions of years. The record will outlast every city, every language, every civilization on Earth. It will outlast the Sun itself. And in all likelihood, no one will ever play it. It is the loneliest object in existence. A love letter sealed in gold, addressed to no one, drifting through the permanent dark. But here is a number that puts all of this in a context that I want you to hold for the rest of this journey. Since the early 20th century, Earth has been leaking radio and television signals into space. Electromagnetic waves traveling at the speed of light in all directions. They have been spreading outward for roughly 125 years. Our radio bubble is 125 light-years in radius. If you placed it on a map of the Milky Way, it would be invisible. not small, invisible, a microscopic dot in a galaxy 100,000 light-years wide. Beyond that bubble, containing perhaps a few thousand stars out of 250 billion in our galaxy alone, no civilization has ever had the chance to detect us. No signal has reached them. No evidence that we exist has ever arrived. We have been broadcasting into the void for a century, and the void has not noticed. We are cosmically silent. And the Milky Way, this galaxy that makes our radio bubble look like a grain of sand, is itself one galaxy among 2 trillion in the observable universe. We did not even know other galaxies existed until 1924. That is not ancient history. That is barely a human lifetime ago. In 1920, the astronomical community held what became known as the Great Debate. On one side, the astronomer Harlow Shapley argued that the Milky Way was the universe. All those fuzzy smudges seen through telescopes, the spiral nebulae, were just gas clouds within our own galaxy. On the other side, Heber Curtis argued that at least some of those smudges were separate galaxies, island universes completely outside our own. The debate was genuine. These were serious scientists with serious evidence on both sides. Neither was stupid. Neither was careless. Edwin Hubble settled it in 1924. Using the 100-inch telescope at Mount Wilson Observatory, he identified a particular type of pulsating star in the Andromeda Nebula, a star whose true brightness could be calculated from how it flickered. He measured the distance. Andromeda was approximately 900,000 light-years away, far too distant to be inside the Milky Way. Later measurements revised the number to about 2.5 million light-years. In one observation, the universe became unimaginably larger than it had been the day before. What had been the entirety of existence was suddenly just one island in an ocean of galaxies stretching in every direction as far as any telescope could see. And that ocean, it turned out, was not smooth or uniform or evenly populated. It had structure, terrifying structure. Empty places of staggering scale and thin glowing threads where matter had gathered, and the whole thing had been slowly assembling itself for 13.8 billion years from quantum fluctuations, smaller than an atom. The universe is not a scattering of stars in empty space. It is a machine, an architecture, and understanding what we are living inside of changes the question of whether anyone else is living here too. Now here is something that should genuinely unsettle you, and I want you to sit with this for a moment before we continue. Most of the universe is nothing. Not sparse, not thin, not nearly empty. Nothing. Or close enough to nothing that the distinction barely matters. In 1981, an astronomer named Robert Kirshner was conducting a routine survey, mapping the positions of galaxies in 3-dimensional space. When he plotted the data for a region near the constellation Boötes, he found a gap. A massive spherical gap in the distribution of galaxies. They rechecked the instruments. They verified the data. The gap was real. The Boötes void, roughly 330 million light-years across. In a region of that size, you would expect to find approximately 2,000 galaxies. The Boötes void contains around 60. Those 60 are not scattered randomly through it. They are clustered along a thin thread running through the middle, like crumbs on a string in an otherwise empty room. The astronomer Greg Aldring once offered a thought experiment that has stayed with everyone who has heard it. He pointed out that if the Milky Way were located at the center of the Boötes void, we would not have discovered that other galaxies existed until the 1960s. Think carefully about what that means. We would have looked out into space with every telescope built before 1960 and seen nothing. No Andromeda, No Magellanic Clouds, no spiral nebulae to debate. We would have believed we were alone in an infinite black sea, and we would have been completely, confidently, permanently wrong. With no way of knowing it, the Boater's void is not strange. It is one example of what turns out to be the default condition of the universe. Voids, enormous spherical regions of below-average galaxy density, make up approximately 80% of the observable universe by volume. 80%. The galaxies and stars and planets that we think of as the universe, the things, are the minority. They exist on the thin walls and filaments between the voids like foam on the surface of a soap bubble. The universe looks, at its largest scale, like foam. Enormous bubbles of near emptiness separated by impossibly thin sheets of matter. And then comes the part that should genuinely stop you. You live inside one of these voids. The Milky Way sits inside what researchers call the KBC void, named after astronomers Keenan, Barger, and Cowie, who mapped it in 2013. It is a region of below-average galaxy density, roughly 2 billion light-years across, 6 times the width of the Boater's void. Our galaxy is not in a bustling cosmic neighborhood. It is in the suburbs where the streetlights have thinned out and the houses are far apart. The cosmic suburbs, 15 to 50% fewer galaxies than in the surrounding space. And we might be near the center of it. This is not just a curiosity. Some researchers believe that living inside a large underdense region might be part of why our local measurements of the universe's expansion rate keep coming out higher than our models predict. Galaxies inside a void are pulled outward gravitationally by the denser regions outside it. This accelerates the local expansion, which means our measuring instruments might be sitting in a slightly unusual spot and giving us a slightly unusual reading. The biggest crisis in modern cosmology might be partly caused by our address. Data presented at the National Astronomy Meeting in 2025 suggested that a void model consistent with our location is roughly 100 million times more likely than a void-free model based on Planck cosmology values. 100 million times. Other researchers dispute this. The debate is ongoing, but the implication is extraordinary. The lens through which we see the universe might itself be the problem. Where did the voids come from? Why is 80% of the cosmos empty? The answer goes back to the first fraction of a second after the Big Bang. The universe was almost perfectly uniform at birth. Almost. Quantum mechanics guaranteed that tiny random fluctuations in density existed everywhere at the smallest scales. Variations of roughly 1 part in 100,000. If the early universe were an ocean, these would be ripples a millimeter high on a surface thousands of kilometers across. But gravity never stops working. And gravity is patient in a way that has no human equivalent. Over hundreds of millions of years, gravity amplified those differences. Regions slightly denser than average pulled a little more matter to themselves. Regions slightly less dense lost matter to their richer neighbors. The rich got richer. The poor got emptier. Dense regions became denser. Empty regions expanded. Over billions of years, the slight variations grew into the vast architecture we see today. Matter gathered into thin sheets and filaments. The spaces between those sheets became the voids. The whole universe, shaped ultimately by quantum jitter at the subatomic scale, organized itself into a web stretching across everything we can see and far beyond. And in 2025, for the first time in human history, we photographed a piece of that web, one thread of it, a single strand of the largest structure in existence, 3 million light-years long, glowing faintly with ancient hydrogen gas, and it looked exactly like the simulations predicted. The The cosmic web is the skeleton of the universe. The term was coined in 1996 by cosmologist Richard Bond, but the idea had been building for years as galaxy surveys in the 1980s and 1990s kept showing the same pattern. Galaxies do not scatter randomly through space. They cluster along invisible corridors. They line up in chains. They gather at intersections. Between those corridors, nothing. The pattern was unmistakable. The universe at the largest scales had organized itself into a three-dimensional spiderweb. Bright filaments connecting massive nodes with dark voids filling the space between. Individual strands can stretch hundreds of millions of light years. They are made of dark matter, gas, and galaxies all pulled together by gravity. At the intersections where filaments meet, galaxy clusters form, the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, vast clouds of superheated gas, enormous halos of invisible matter. Our own local group, the small collection of about 100 galaxies that includes the Milky Way and Andromeda, sits on one of these filaments. Not at a node, not at an intersection, on a back road between two galactic cities. For decades, the cosmic web existed only in computer simulations and mathematical models. Supercomputers consistently produced web-like structures matching what galaxy surveys observed. The theory was solid, but directly imaging a filament, capturing the actual faint glow of the gas within it, was like trying to photograph a candle flame from the other side of a continent. Then, in 2025, an international team led by a doctoral student at the University of Milan Bicocca, working with the Max Planck Institute for Astrophysics, achieved what a generation of astronomers had hoped for. They used an instrument called MUSE, mounted on the European Southern Observatory's Very Large Telescope in Chile. MUSE collects spectra for every pixel in its field of view simultaneously, allowing astronomers to separate the filament's faint hydrogen emission from background noise. But even with that instrument, the task required over 150 hours of observation focused on the exact same patch of sky. 150 hours of the world's most powerful telescope staring at a single point, gathering one photon at a time. The resulting image showed the filament stretching 3 million light-years between two galaxies, each hosting an active supermassive black hole, their combined radiation illuminating the gas of the web connecting them. When they compared the image to supercomputer simulations from the Max Planck Institute, the agreement was stunning. The shape, the density, the brightness profile of the observed filament matched the predictions almost exactly. The models had been right all along. We have a photograph of the cosmic web now. We are no longer inferring it from the distribution of galaxies. We have seen it. And just before we leave the web and go deeper, I want to ask you something. Stop scrolling. Stop checking your phone. And really ask yourself this, because I genuinely want to hear your answer in the comments. Knowing that the structure of the universe looks like a three-dimensional spiderweb, built from the amplified echoes of quantum fluctuations a fraction of a second after the Big Bang, does that make reality feel more or less real to you? More or less meaningful? I will tell you what it does to me at the end. But first, we have to talk about what the web is actually made of. And this is the part of the story that should keep every physicist on the planet awake. Because the web is not built from anything we understand. 85% of all the matter in the universe is made of something that emits no light, absorbs no light, reflects no light, and has never been directly detected by any instrument ever built. We know it exists only because gravity tells us it is there. 5%. That is the fraction of the universe made of the matter you learned about in school. Protons, neutrons, electrons, atoms, molecules, stars, planets, every human being, every ocean, every mountain, every machine, every instrument we have ever built, every photon we have ever captured. All of it, together, makes up 5% of what the universe contains. 27% is dark matter. 68% is dark energy. Together they constitute 95% of everything that exists, and we do not understand either of them. Dark matter was first proposed in the 1930s by Fritz Zwicky, a Swiss astronomer studying the Coma cluster, a massive collection of galaxies about 320 million light-years from Earth. He measured the speeds of the galaxies moving through the cluster. They were moving far too fast. The visible matter in the cluster could not possibly generate enough gravity to hold them together. They should have flown apart billions of years ago. Something invisible was providing the extra gravitational force. Zwicky called it Dunkel Materie, dark matter. For decades, the idea was largely ignored. Too strange, too speculative. Then, in the 1970s, astronomer Vera Rubin made the same discovery on a different scale. She was measuring the rotation speeds of stars within spiral galaxies. According to Newtonian gravity, stars at the edge of a galaxy should orbit more slowly than stars near the center, just as outer planets in our solar system orbit more slowly than inner ones. Rubin found that the rotation curves were flat. Stars at the edges of galaxies were moving just as fast as stars near the center. The only explanation was a massive invisible halo of matter extending far beyond the visible disk of every galaxy she measured, providing the gravitational pull needed to keep the outer stars from flying away. Since then, the evidence has accumulated from every direction. Galaxy clusters bend light from objects behind them far more strongly than their visible mass can explain. The cosmic microwave background contains patterns that only make sense if dark matter existed in the early universe to create the gravitational wells into which ordinary matter could fall. The cosmic web itself would not form without it. Simulations using only ordinary matter produce universes that look nothing like what we observe. Add dark matter and the web emerges. The filaments form, the voids open, the galaxies cluster. Dark matter is not a minor ingredient. It is the main ingredient, 85% of all matter in the universe, and we have never found the particle. Dozens of experiments are searching. Underground detectors in abandoned mines, shielded by kilometers of rock. Particle accelerators smashing protons at nearly the speed of light, hoping to create dark matter in the collision debris. Space telescopes scanning for gamma-ray signatures, nothing confirmed. After decades of searching, we can map dark matter's distribution across the universe, measure its effects on everything around it, but we cannot identify what it actually is. In 2024, researchers used data from the Subaru telescope to achieve the first detection of dark matter sitting directly on cosmic web filaments in the Coma cluster region. They used gravitational lensing to map the dark matter distribution along the strands of the web. It was there, right where the models predicted, invisible but heavy, shaping everything, weighing more than all the visible matter combined, present everywhere and nowhere we can touch. Now, dark energy. In 1998, two teams of astronomers made a discovery that won them the Nobel Prize and overturned the foundational assumption of cosmology. They were using a specific type of exploding star, Type 1, A supernovae, as cosmic distance markers. These explosions all reach roughly the same peak brightness, which means measuring how bright they appear from Earth lets you calculate how far away they are. both teams were using these supernovae to measure the expansion history of the universe. The assumption going in was simple. The expansion must be slowing down. Gravity attracts everything to everything. The expansion should be decelerating. It was the obvious prediction, and essentially everyone believed it. The distant supernova were dimmer than expected. They were farther away than they should have been. The expansion of the universe was not slowing down. It was speeding up. Something was pushing space apart. Something was overcoming the gravitational attraction of all the matter in the observable universe and accelerating the expansion. Something with no known mechanism, no obvious source, no precedent anywhere in physics. They named it dark energy, not because it was energetic in any intuitive sense, because it does something, and that something appears to be tearing the universe apart. Dark energy is not a force in the conventional sense. It does not push galaxies away from each other the way wind pushes a sail. It is a property of space itself. It causes space to expand. And the more space there is, the more dark energy there is, which causes more expansion, which creates more space. It is a feedback loop with no ceiling. And it is winning. The consequences are profound and permanent. There are galaxies receding from us right now faster than light, not traveling through space faster than light. That is impossible under relativity. But being carried away by the expansion of space itself, which has no speed limit. Light emitted from those galaxies right now, aimed directly at us, will never reach us. The photons leave their source at the speed of light and begin crossing the space between us and them. But that space is expanding faster than they can cross it. They fall behind. They never arrive. Those galaxies are lost to us not because they are far away, but because the distance between us and them is growing faster than light can travel. This creates a boundary, the cosmic event horizon. Everything beyond it is and forever will be completely disconnected from us. No signal can cross it. No message, no light, no gravitational wave. Nothing. Not now. Not ever. The universe is not just vast. It contains regions that are permanently, causally unreachable. Regions we cannot see, cannot communicate with, cannot interact with in any way. And dark energy is guaranteeing that this boundary grows tighter over time, swallowing more of the universe, sealing more away. Over trillions of years, the expansion will carry distant galaxy clusters beyond that horizon. They will redshift into invisibility. They will fade from our sky one by one, like ships sailing over the horizon of an ocean that is growing faster than any ship can sail back. In the far future, the only galaxies visible to any observer will be the few dozen in our local, gravitationally bound group. The rest will be gone, not destroyed, just unreachable. In that distant age, a civilization looking up at the sky will see a single galaxy in an infinite black void. They will have no way of knowing that trillions of other galaxies once existed. The evidence will have been carried away by the expansion of space. Their cosmology will be wrong through no fault of their own. We live in a rare and fleeting moment. Right now, today, we can still see the cosmic microwave background. We can still detect ancient light from a universe less than 1 billion years old. We can still piece together the story of how everything began. That window is closing. The universe is slowly, inexorably hiding its own history. We need to talk about what the most powerful telescope ever built is showing us, because it was supposed to confirm our understanding of the universe. Instead, it has shattered it. The James Webb Space Telescope launched on Christmas Day 2021. 25 years in development, $10 billion, a 6.5-meter gold-plated mirror designed to capture infrared light from the earliest moments of cosmic history. In January 2026, NASA confirmed the detection of the most distant galaxy ever observed. It is called MOM-Z14. Its light has been traveling toward us for over 13.5 billion years. We are seeing this galaxy as it existed just 280 million years after the Big Bang, when the universe was 2% of its current age. 2%. And it should not look the way it does. According to every model that existed before Webb launched, galaxies at this epoch should be dim, small, primitive collections of primordial gas just beginning to form their first stars. The universe at 280 million years old had simply not had enough time for anything complex to exist. Not enough time for large-scale star formation. Not enough time for heavy elements to accumulate through stellar generations. Not enough time for galaxies to grow bright and structured. MOM-Z14 defies every one of those expectations. It is remarkably luminous. It is extraordinarily compact. Its spectrum reveals elevated levels of nitrogen, an element that normally requires multiple generations of stars to produce, because massive stars fuse hydrogen and helium, explode as supernovae, scatter heavy elements into surrounding gas. New stars form from that enriched material. Process repeats. Nitrogen accumulates. Multiple stellar generations, which takes time. More time than 280 million years allows. The research team proposes that supermassive stars, far more massive than anything in the modern universe, may have formed in the dense chaotic environment of the early cosmos and produced nitrogen through nuclear processes that normal stellar evolution cannot achieve on this timeline. And beyond the chemistry, MOM-Z14 appears to have already partially ionized its surrounding environment. The early universe was filled with neutral hydrogen gas, a fog that blocked ultraviolet light. Most models say that at this epoch the universe should still be nearly entirely opaque fog. This tiny galaxy, barely 240 light-years across, 280 million years after the Big Bang, has already begun clearing the fog around it. Something the models said was impossible at this point in history. Rohan Naidu, the lead researcher at MIT, put it plainly. With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted. And MOM-Z14 is not isolated. It is the most extreme example of a pattern. Webb has found over 100 bright galaxies at redshifts above 10, in an era where pre-launch consensus models predicted essentially none. The number density of bright galaxies at this distance is more than 100 times larger than those models expected. Not 10% more, not double, 100 times. Among these findings is a galaxy called Zhulong, a galaxy at a redshift of about 5.2, meaning we see it as it was roughly 1 billion years after the Big Bang. It has spiral arms, a mature central bulge, a total stellar mass of about 100 billion solar masses. It looks like a galaxy that has had billions of years to settle and grow. It had 1 billion. Galaxies like this are not supposed to exist that early. Spiral structure requires dynamical settling. Central bulges require repeated mergers and extended accretion over long periods. Assembling 100 billion solar masses of stars in 1 billion years is at or beyond the limit of what star formation physics should allow. And yet, there it is, fully formed, impossibly mature. Jacob Shen, a researcher at MIT, described the mood of the field in terms that, from a scientist, land hard. There is a growing chasm between theory and observation related to the early universe, a growing chasm. That is how cosmologists describe a crisis. To be completely clear, the Big Bang is not in question. The evidence for a hot, dense origin is overwhelming and comes from multiple completely independent sources. The cosmic microwave background, the ongoing expansion of space, the abundance of light elements like hydrogen, helium, and lithium, which match Big Bang nucleosynthesis predictions with extraordinary precision. These pillars are solid. What is breaking is the timeline. What is breaking is the sequence of events our model predicts should follow the Big Bang. Galaxies forming too fast, too bright, too massive, too structured, too old when they should be young. The Lambda CDM model, the standard model of cosmology, has survived every challenge for a quarter century. It may now be genuinely failing, not because of a math error, because the universe, when we finally looked at it with adequate instruments, is not doing what we told it to do. Proposed solutions are multiplying. Early dark energy, a brief burst of extra dark energy in the first few 100 million years that would have accelerated structure formation. Modifications to how dark matter interacts with itself. New particle physics entirely. None fully works, none explains all the anomalies without creating new problems. In 2025, a conference called Tensions in Cosmology brought over 130 researchers together in Corfu, Greece, to address the growing list of discrepancies. The conference report published in Nature Astronomy stated clearly, this is not a minor correction to an otherwise healthy model. This could require new fundamental physics. Which brings us back to the Hubble tension, because these crises are not separate. They are symptoms of the same thing. Our map of the universe, the one we spent the last century building, is contradicting itself, and the telescope we built to resolve the contradictions is instead deepening them. Let me take you somewhere that has no scientific controversy at all. It is simply the truth of where you are and how you got here, layer by layer, each container impossibly larger than the one before it. You are on Earth, a rocky planet 12,742 kilometers in diameter. It orbits the Sun, a middle-aged yellow dwarf star, roughly 4.5 billion years old. The Sun is one of 250 billion stars in the Milky Way. It is not special. It is not large. It is not centrally located. It is an ordinary star in a minor spiral arm called the Orion Spur, roughly halfway between the galactic center and the outer edge. The Sun and its planets make up the solar system. The solar system sits within a small region of diffuse interstellar gas called the local interstellar cloud, about 30 light-years across. The local interstellar cloud sits inside the local bubble, a region of hot low-density gas roughly 1,000 light-years across, inflated by a series of supernova explosions over the last 10 to 20 million years. The local bubble sits within the Orion Arm, which connects two larger spiral arms of the Milky Way. The Milky Way is a barred spiral galaxy 100,000 light-years in diameter, 1,000 light-years thick at the disk, containing 250 billion stars. At its center sits a supermassive black hole called Sagittarius A star, with a mass roughly 4 million times that of the Sun. The Milky Way is one of about 100 galaxies in a gravitationally bound structure called the local group, spanning 10 million light-years. Its two largest members are the Milky Way and the Andromeda Galaxy, which contains approximately 1 trillion stars and sits 2.5 million light-years away. These two galaxies are on a collision course. In roughly 4.5 billion years, they will begin merging in a slow gravitational dance that will reshape both entirely. Most stars will not collide. The distances between individual stars are too vast. but the galaxies themselves will be transformed into something new. In about 7 billion years, the merger will be complete. The resulting structure may be an elliptical galaxy. Astronomers have already named it Milkomeda. The local group is a member of the Virgo supercluster, roughly 100 galaxy groups, and clusters spread across 110 million light-years. At its heart is the Virgo cluster, over 1,300 galaxies, 54 million light-years from Earth. But the Virgo supercluster is itself just a lobe of something vastly larger. In 2014, astronomer Brent Tully and his team published a paper that redrew the cosmic map. Using galaxy flow data, mapping the gravitational basin in which the Milky Way and thousands of other galaxies reside, they identified a structure containing approximately 100,000 galaxies spanning 520 million light-years. They named it Laniakea, Hawaiian for immense heaven. The Great Attractor, the gravitational anomaly pulling the Milky Way at 2 million kilometers per hour, sits at Laniakea's center. We are inside Laniakea. We are falling toward its center. And we will never arrive because the expansion of space is carrying everything apart faster than gravity can pull it together. Laniakea is part of the Pisces-Cetus supercluster complex, one of the largest coherent structures ever identified, approximately 1 billion light-years long. 1 billion light-years. A thread of galaxy clusters strung along a single filament of the cosmic web. And all of this, the Pisces-Cetus supercluster complex, Laniakea, the Virgo supercluster, the local group, the Milky Way, the Sun, the Earth, is a tiny fragment of the observable universe. The observable universe is a sphere centered on Earth with a diameter of approximately 93 billion light-years. It contains 2 trillion galaxies, 10 to the power of 24 stars, more stars than every grain of sand on Earth combined. The Pisces-Cetus supercluster complex, one of the largest structures we know, is roughly 1% of the observable universe's diameter. 1% of what we can see in a universe that we can barely see. Think about what that means before we go any further. Pause this right now and actually try to picture that. Try to picture a thread of galaxies spanning 1 billion light-years and understand that it is 1% of the observable universe, and the observable universe is itself potentially 1/15,000,000th of the full cosmos. Try to hold all of that at once. You cannot. The human brain is not capable of it. And yet we measured it. That is what we are going to talk about next, because 93 billion light-years sounds like everything. It sounds like the end. It is not even the beginning. The observable universe is not the universe. It is the part of the universe from which light has had time to reach us since the Big Bang. There is more beyond it, vastly, unfathomably more. And we know this because of a single measurement, one property of the universe confirmed to extraordinary precision. The universe is flat, not flat as in shaped like a table, flat as in geometrically flat. In a flat universe, the angles of a triangle add up to exactly 180 degrees. Parallel lines stay parallel forever. Space does not curve back on itself. In a positively curved universe, like the surface of a sphere, parallel lines eventually converge, and you could, in principle, travel in a straight line and return to your starting point. The universe would be finite and unbounded like a balloon. In a negatively curved universe, like the surface of a saddle, parallel lines diverge, and angles in a triangle add up to less than 180 degrees. Measurements from the cosmic microwave background and from baryon acoustic oscillations The fossilized sound waves from the early universe imprinted on the large-scale distribution of galaxies tell us the universe is flat to within 0.4%, essentially perfectly flat. And this has one staggering implication. The only way our 93 billion light-year observable patch can appear perfectly flat is if the total universe is vastly, overwhelmingly larger. In the same way, a basketball court appears flat because the curvature of the Earth is too gradual to detect at that scale. Researchers at Oxford analysing curvature constraints from the CMB concluded the universe is at least 250 times larger than the observable portion, at minimum. The full universe, by this conservative estimate, would be at least 23 trillion light-years in diameter. Its volume at least 15 million times what we can see. Everything we have discussed tonight, every galaxy, every void, every filament, every measurement ever made by every telescope ever built, all of it fits inside a volume that is at best 1/15 millionth of the whole. And that is the conservative estimate. Alan Guth, the physicist who proposed cosmic inflation in 1980, has calculated based on inflationary models that the total universe could be 10 to the power of 23 times larger than the observable portion, 100 sextillion times. If the observable universe were shrunk to the size of a coin, the full universe under Guth's estimate would be a sphere more than twice the diameter of the Milky Way. And some inflationary scenarios suggest the universe is literally infinite. Not very large, not incomprehensibly large, actually infinite, extending forever in every direction with no boundary, no edge, no center. If the universe is infinite, then every possible arrangement of matter occurs somewhere, not as metaphor, as mathematical necessity. In an infinite universe with finite possible configurations of matter, every configuration that can happen does happen, including somewhere impossibly far beyond our observable horizon. An exact physical copy of you reading this exact sentence, thinking this exact. That is either exhilarating or paralyzing depending on your temperament. But regardless of whether the universe is 250 times larger, or 10 to the 23rd times larger, or infinite, one thing is certain. We will never see most of it. The cosmic event horizon seals us in permanently. The accelerating expansion ensures that the vast majority of what exists is and always will be beyond any possible instrument, not just far away, causally disconnected, gone in every sense that matters to physics. We are inside a fishbowl floating in an ocean whose shores we will never see. And if space can inflate once, it can probably inflate again, elsewhere, eternally. The theory of eternal inflation proposes that our Big Bang was not the beginning of everything. It was a local event, one pocket of space where inflation happened to stop, where conditions happened to be right for particles and forces and eventually for everything. But outside our pocket, in regions so far beyond our horizon that the word distance loses its meaning, inflation may still be going, may always be going. The quantum field that drove the expansion in our neighborhood may be driving it in others right now. If inflation continues eternally, then bubble universes constantly nucleate within the inflating space. Each bubble, a pocket universe with its own Big Bang, its own initial conditions, its own history, including, in some models derived from string theory, its own physical constants, different strengths of gravity, different masses for electrons, different numbers of spatial dimensions, 10 to the power of 500 possible configurations of physical law. Each bubble a different universe with different rules. This is the multiverse, not the science fiction version, the physical one. an infinite collection of causally disconnected pocket universes, each expanding independently, each inaccessible to every other. No signal can pass between them. No light, no gravity, no information. They are islands in an ever-expanding sea of inflating space. The multiverse remains at the edge of what science can currently test. Its critics argue that a theory predicting everything predicts nothing. If any physics is possible somewhere, nothing is falsifiable. Proponents counter that eternal inflation is not a speculative add-on. It is a nearly unavoidable mathematical consequence of the same inflationary theory that the CMB data confirms. You cannot accept the part of the theory that explains why the universe is flat and then reject the part that implies other universes. The mathematics does not allow it. Before Stephen Hawking died in 2018, he co-authored a paper proposing a way to constrain the multiverse using the holographic principle, potentially making it testable through gravitational wave astronomy. The work is unfinished. The question is open. And it will likely remain open for longer than our civilization has existed so far. Now we have the numbers. Now we have the structure. Now we have the scale. And we have to ask the question. In all of this, 2 trillion galaxies, 10 to the 24th stars, billions of trillions of potentially habitable worlds, a universe that may be 15 million times larger than what we can see, possibly infinite, possibly one of infinite others. In all of that, is there anyone else? Is there anything out there that looks up at its sky and wonders the same thing? The numbers say yes. The silence says nothing. Conservative estimates place the number of rocky planets in habitable zones in the Milky Way alone at between 300 million and 10 billion. If we scale that up to 2 trillion galaxies, the number of potentially habitable worlds is in the billions of trillions. Scale further to the full universe, and the number becomes meaningless. The probability that Earth is the only planet where life arose, given all of that, seems not just small, but absurd. Unless the leap from chemistry to life is so improbable that even with billions of trillions of chances, it has happened exactly once. We do not know. We have a sample size of 1. A single data point tells you nothing about probability. Life could be everywhere. We could be the only ones. Both are consistent with everything we currently know. But if life is not rare, then the silence is deafening. In 1950, Enrico Fermi was having lunch with colleagues at Los Alamos. The conversation turned to extraterrestrial civilizations. Fermi thought through the numbers, the age of the galaxy, the number of stars, the probability of planets, the time it would take a spacefaring civilization to colonize the galaxy at even modest speeds. Even at a fraction of the speed of light, a single civilization could spread across the entire Milky Way in a few tens of millions of years. Tens of millions of years is nothing. The galaxy is over 10 billion years old. Civilizations have had time to colonize it hundreds of times over. And there is no evidence that anyone has. No confirmed signal, no artifact, no megastructure visible in our telescopes, no visitation, no electromagnetic fingerprint of technology in the sky. Nothing. Where is everybody? The Fermi paradox, 75 years old and still without an answer. The explanations are numerous. The Great Filter, a barrier somewhere between dead chemistry and a galaxy-spanning civilization, so difficult that almost no species crosses it. If the filter is behind us, we are among the vanishingly rare who made it through. If the filter is ahead, civilizations commonly arise, but always destroy themselves before becoming interstellar. Our future, in that scenario, is already written. The zoo hypothesis advanced civilizations exist but deliberately leave us alone, watching without interfering. The dark forest theory. The universe is dangerous. Every civilization that reveals itself risks destruction, so all the advanced ones have gone silent, hidden, listening but never speaking. We are doing exactly what every naive young civilization does, broadcasting loudly into the dark, announcing our presence to anyone who might wish us harm. And then there is the explanation that requires no conspiracy, no filter, no strategy, just architecture, distance. Everything in this documentary has been building toward this. The cosmic web separates galaxies along filaments spanning hundreds of millions of light years. The voids between them are chasms of near-nothingness. The expansion of space is accelerating, carrying clusters apart faster each year. The cosmic event horizon permanently seals off most of the universe. Even within our galaxy, the distances paralyze. The nearest star is 4 light-years away. A radio signal sent today takes 4 years to arrive. A response takes another 4. 8 years for a single exchange, if both civilizations survive long enough to complete it. Our radio signals have traveled 125 light-years. A sphere 125 light-years in radius in a galaxy 100,000 light-years wide. A whisper in a cathedral. Beyond that bubble, no civilization has had the chance to hear us. No evidence of our existence has arrived at their sky. The Andromeda Galaxy is 2.5 million light-years away. A message sent there today arrives in 2.5 million years. The species that sent it will be long extinct before any reply returns. Communication across the cosmic web is not merely difficult. It is functionally impossible on any timescale relevant to biology, any timescale relevant to civilization. This may be the answer to the Fermi paradox. Not that intelligence is rare, not that civilizations are self-destructive, not that anyone is hiding, but that the universe is too large, that the architecture itself is a quarantine. Every civilization is an island, and the ocean between the islands is so vast that no message, no ship, no signal can bridge it in any time that matters. The universe may be full of voices, every one of them calling into the same silence, every one of them unheard. And we are still here, still looking, still asking. Before you go, I genuinely want to know 2 things from you in the comments. The first, which moment in this journey changed something in how you see reality? Not just surprised you, actually changed something. And the second, do you think the fact that we are the universe observing itself makes our existence feel more meaningful? Or does the scale make it feel more fragile? Because I think both answers are right. And I think the tension between them is exactly what it feels like to be alive and aware on a pale blue dot in an immense heaven. If tonight changed how you see the sky, share it with someone who needs to look up. Like this video so others can find it. Subscribe if you want to keep going deeper. We are just getting started. The universe is not out there. It is something you are part of. And every question you ask about it is a question you are asking about yourself. Thank you for making it to the end of the universe with us. We will see you in the dark.